Talked about sending humans to Mars.
Yes.
Why send humans when on the same budget you could send many robots?
Right. So Curiosity has been on the surface for 5 years, and if a human was doing that job, it would probably do it in a day. Okay. Let me tell you top speed of Curiosity. Here it is. That's top speed. Okay? That's flat out. All right? Not only that, we're anywhere from 4 minutes to 22 minutes away from a signal from Mars, based on where it is in its orbit. We can't joystick it, all right? We have to give it a command. We have to tell it, okay, move in this direction. It has some AI software that as it moves, if the wheel spins, it stops. That means it's in a dusty area that we didn't anticipate. It could get trapped. You know, and so the interaction is very difficult. We have anywhere up to 60 people in a room planning out how it can move for 120 meters. Okay? Now, there's no substitute for a robotic measurement that these things can make. They can make some spectacular measurements, but humans could actually do a quicker job and can actually make decisions quicker, can anticipate, deploy instruments. It can anticipate, oh, I've been here, I've seen this rock, I know what these are like, and they're the same over here. I don't need to sample that, I can move on. So the decision-making capability of humans still outstrip our robotic missions. But yet, we have to send the robotic missions first. It's not Star Trek. It's not go where no human has gone before, okay? We can't possibly send humans there and expect them to survive when we don't know the environment. And so our robotic missions absolutely have to lead, but humans will follow. And when they do, they'll be able to do much more science. So we really want them to go because we want to, as scientists, go with them. Okay? So we need, the gentleman needs a pen, right? Yeah. Okay, he's got one. Great, 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 great. Man.
If Voyager runs out, well, when will Voyager run out of fuel?
Yeah,
and
great question.
It will stop.
Yeah, yeah. We're hoping to get maybe the next 5, maybe 8 more years out of it. The problem is it was never designed to do this. It had a certain amount of radioactive material that generates heat, and then we take that heat and with what's called a thermoelectric, have a voltage difference, charge a battery, and then that battery we run all our experiments. So as the radioactive material dies away over time, its power will continue to decline. And right now, it's generating about enough energy as a 10-watt light bulb, okay? And yet we can see it with our radio antennas, and it is 135 astronomical units away. It is really out there, okay? And it's really remarkable that we can do that, but right now it's possible. The next one, follow-on, Voyager 1 and 2, is indeed New Horizons. That will last into the 30s, and we're hoping to get it into the 40s. And it will punch through the heliopause, and we'll start making some new fabulous measurements of winds of other stars. Okay. Yes?
You mentioned that Mars lost its magnetic field in the past, leading to rapid climate change. What are the prevailing theories as to why this happened, and is there any experiments going on right now as to give us a factual answer?
Yeah, we really don't know, okay, but we always have, we always have ideas. We always have models, And I believe a major impact disrupted the currents on the core, on the outer core of the planet, where the currents are generating the magnetic field. And once it gets disrupted, it's almost impossible. It's impossible. We don't know how to restart them. And I think that impact is what did it. And I think that impact is Hellas Basin. that huge blue area that you may remember in the one Mercator projection in the lower right-hand corner. It's just a huge impact, and it comes at about that time. But I'm probably wrong. I'm wrong a lot when I speculate. But that's, you know, in my opinion, that's probably our best shot at it. We just don't know. Now, what's really exciting is the InSight spacecraft and the ExoMars rover both have magnetometers on it. And so they'll be making magnetic field measurements, and that may be important for us to be able to use to understand a little bit better about perhaps how the field is changing over time, and get an idea of why it lost it. Okay? Okay. Yes, sir.
After this small boy, I have to tell you, welcome. I am the older here in this room, and I am honor president of Cyprus Association of Astronomy. And I am very glad to hear you, and I wish you good luck to all the missions to find the rest of the stars.
Thank you.
Thank you.
Yeah, so let me, thank you very much. I want to find life beyond Earth, and we're on the hunt for it, and we're making enormous progress. I believe in your lifetime, you know, we will answer the question, are we alone? Okay?
What do you think?
Oh, you want me to answer it for you? Okay, I will. Sometimes people don't ask me to answer that. So once again, I'm going to give you my best estimate. And I think we'll find life in the solar system first before we find it on exoplanets, but we'll find it there too. And we'll then realize that the galaxy is teeming with life, and it will change everything. Okay, that's what I believe. Yes, sir.
You mentioned that we're sending a satellite to orbit the sun. I can think that we expect this satellite to come back, so it will crash into the sun's atmosphere at the time. What will happen then? Will it affect?
That's a really good question. So right now there's a number of possibilities, but what we're focusing on is to continue to get it into the orbit and make sure everything is right. We will take our first pass in November, coming up. It's a matter of weeks from now. We're going to take our first pass around the sun. But that spacecraft, so long as it remains healthy, will continue to do that. And once it runs into problems and ends up aging, we'll then make a determination what we need to do. Now, it's in an area that it's not going to hit a planet where there might be life on it. And so it's in a pretty, you know, as far as it goes, more than likely, we'll just turn it off. Once it's nearly dead, or it could die on us, you know, because of solar flares. A solar flare could just hammer it, take it out. Okay, could happen. We don't want that to happen, but it could happen. And that'll be it, and that's okay because it's not gonna affect anything else. Okay. All right. Let me work up the chain here. All right. Yes, sir.
So you mentioned that we'll be growing plants on Mars in order to create a sustainable environment.
Sure, didn't you see The Martian?
So I read somewhere that Martian soil contains something called perchlorates.
Yes.
Sodium perchlorate, which
Right.
is highly toxic.
Right, on the surface.
Yeah.
Right.
So my question is, can we eliminate, can we get rid of
yeah,
those?
we can.
Or
We scrape off the perchlorates, and then when we get into the soils, where curiosity is right now, the soils are alkaline, which means we can grow beans and asparagus. Okay. So there's going to be areas where those soils will be more acidic, where we could grow potatoes. But if you watch the movie The Martian, I think if he was where Curiosity was and he had to grow asparagus, if it was me, I'd just take my helmet off and walk outside. I don't know that I could eat 2 years worth of asparagus. Potatoes I could do, but not asparagus. But indeed, we're studying that right now. There's a group in Japan that is trying an experiment of growing trees in a Martian environment where it's low pressure, dominated by carbon dioxide, and the trees they picked are poplars, okay? And they know an enormous amount about the genetic makeup of the poplars, and they think they'll be able to do that. If they can start growing poplars in that kind of environment, we might be planting, poplar forests on Mars before we show up. And that will be a tremendous resource. Poplars will change the climate. They breathe in CO2 and exhale oxygen. And that's a great start. As I mentioned, we are the first species on this planet that can leave it and explore and go out into the solar system. The solar system is ours. It's humanity's. Let's explore it together. Let's get out there. We really need to study these things. Sure. Yes, sir.
Yeah, my question lacks scientific background, or it's clearly for me to get a pin. I just wanted to ask if how many songs are recorded on the golden plate of Voyager 1, and if Chuck Berry really is on that plate.
Yeah, good question. So, Carl Sagan was asked by NASA to create a record of sounds. And he did. He brought a team together, and there's on the order of 100 sounds or so. And there were also images too, that can be that are encoded and can be recovered from it. And indeed, that record is a duplicate for both Voyager 1 and Voyager 2. And Carl wrote a book about that, of his adventure doing that, and then talks about each and every one of the images and sounds, and then the rationale behind why they chose those. There's one image that he wanted on that NASA rejected, okay? And it's an image of a naked man and a naked pregnant woman. And it's very tasteful, and but NASA rejected that. I wasn't working for NASA at the time. Don't blame me. But that's in the book. That's in the book, okay? Yes, ma'am.
So first off, thank you for coming. I think it's truly amazing that Cyprus, University of Cyprus, and NASA can partner and have this summit.
My pleasure. It's a beautiful country. I love it.
Yes. I also have a little bit of a different question. So as you know, the Trump administration cut NASA's budget. With that said, how do you feel this will impact the future of space exploration and new missions and learning how these planets correlate to this Earth?
Right. Okay, so let me be clear. The Trump administration did not cut NASA's budget. NASA's science budget is higher than I've seen it in the last 15 years. Planetary science is greater than it's ever been. This year, our budget is $2.2 billion, okay? Planetary alone. The rest of the science organization totaled up is about $5 billion. NASA has a very healthy budget, and the Trump support has been outstanding. And that includes Earth science. Earth science also has a healthy budget, okay? Take my word for it. Okay, so let me go over here. Yes, sir.
So, what could you do if you got a much higher, like, say, 50 billion budget? How much further in the future? Like, what would you be able to build?
Good question. So our budget is right around 20 billion right now, okay, which is an all-time high over the last 20 years. It's just a fabulous budget. More than doubling that would be spectacular, except for one thing. I feel we wouldn't be able to spend the money efficiently. It's too much money. We really need to be able to obtain funding that increases over time, that allow us to build capacity, that allow the next generation to be identified and brought in. We have plenty of things to do, but if we have too much money, we can't spend it the way we want to. We don't want to waste it. You know, the public has given NASA the funding, as the other agencies, you know, obtain funding from their public. And we need to give them the value for their money, okay? Now, I think the things we do in space is a tremendous return on their investment. But there'll come, when there's too much money, then we really can't be sure that we'll be able to spend it appropriately, okay? But we could do amazing things with $50 billion. All right, let's move up the row. Yes?
As far as I know, New Horizon will have a visit to a Kuiper Belt object this New Year's. New Year's.
Yep.
Ultima Thule or something like that.
Yep.
As a scientist, do you think that it will surprise us as Pluto did? And do you have further plans for New Horizons?
Yeah, so I have no doubt when we fly by Ultima Thule on January 1st that we'll be shocked. Okay, I'm now waiting for it. And the reason why is we're flying by a very small Kuiper Belt object. It's about 30 kilometers in size. It's a building block of Pluto. A bunch of them got together and made Pluto. I have no idea what this thing's going to look like. I have no idea what the composition and surface structure. And in fact, there's some indications that it's not round, but it's oblong. And in fact, there's some indications that it may actually be two objects. I mean, this is just really bizarre. But we're going to fly by that puppy, and we're going to get really close, and we're going to have some fabulous images. And it will change our thinking, for sure. It's then going to continue on through the Kuiper Belt. There may be another Kuiper Belt that it can fly by, but we haven't identified it. But it's going to go out to the heliopause and beyond. So that's what will happen. Okay, let me keep going up the row. Yes, sir.
For the New Horizon, are you able to upgrade some of the software that it has to help you do more things with it?
Yeah, New Horizons has computers on it that actually are probably 3 orders of magnitude more capable than the Voyagers. I mean, it's just a huge generational leap. They're tremendously versatile. And they've already been reprogrammed several times to do things that I would have thought couldn't be done. And that's going to continue. I mean, the teams that are working on New Horizons are just, some of the top people in the world. It's just really exciting to work with them. Okay, yes, sir.
SpaceX and Elon Musk are planning by 2024 to send humans at Mars to build bases for future flights. And they're also like envisioning built-in civilization. Do you think by 2024 is that possible? And what part NASA will take in this mission?
So Elon's doing fantastic. He's building all kinds of rockets. He's incredibly creative. We want to help him be successful any way we can. Right now, we have what we call a Space Act agreement with Elon. Now, he's never gone to Mars before, Going to Mars is tough. We have about 52 missions that have gone to Mars for which only half of them have worked. The other half have been failures, okay? So Mars is hard in a whole bunch of ways. So our agreement would be if Elon's going to Mars, get him to the top of the atmosphere, then it's all him from there on, okay? And we want him to be successful. It's those kind of efforts that enrich our overall program, because he'll be using a variety of different techniques, doing different methods that may be better than the way we are doing it. You know, there's not just one way to do things. There's multiple ways. And so the more creative we can be, and the more, and how we can bring in these other views is by bringing in people from other cultures. They all have, everybody has different perspectives. This is why it's so important that we leverage that ability in this world to bring in a diverse set of cultures to think about things differently. So we wish him luck, and we'll see what happens. All right, let's go to the next row. Yes, sir.
So a bit of a hypothetical question.
Yes.
So if the time to travel to any other body in the solar system was not an issue, and if NASA had time to prepare, what would be the top 5, your top 3, say, planets to explore first?
Sure. So let me tell you the top 2. We would continue to go to Europa, and we do the things that we want to do, but the ones we haven't really been to and studied very much, you didn't hear much about. In fact, you didn't hear anything about it, and that's Uranus and Neptune. Uranus and Neptune are what we call ice giants. Now, they're not like the gas giants. They actually have, Jupiter and Saturn, they actually have very different compositions. In fact, I believe their difference in composition is because they've eaten up a whole slew of Kuiper Belt objects, because they're sitting out there and they're probably eating them up, you know, particularly early on. And that's changed overall their composition. And they are really weird. I mean, their magnetic field structures and how they spin, you know, we really got to get out there. And it's only been the Voyagers that have seen them. It's only been the Voyagers that have seen them. Okay. Yes, sir. Your hand's been up, and it's now your turn.
Anymore, but I'm going to ask my question. I still remember it. Okay. You talk about this kind of large-scale weather phenomena, planets losing their atmosphere over hundreds of thousands of years.
Yeah.
And I'm riding my bicycle with my children here, trying to save the planet from global warming. So, from NASA's point of view, when you hear all this discussion about man-made phenomena, do you think this is just background noise in the overall scheme of things, or there is value to me riding the bicycle?
Yes, this is really good discussion, and it's very timely. So I'm a planetary scientist, and so when we look at things, we look over a long time record. The Earth is 4.6 billion years, and I can tell you emphatically that the climate on this planet has done nothing but change, and it will continue to change, okay? And so it's not about the fact that it's changing, it's got to be about the fact of the rate of change. Life evolves on this planet based on the environment that it's in. There's actually a symbiotic relationship between how this planet evolves and how life evolves on the planet. And they're connected. So as the world gets hotter, we will have to learn to live in a hotter world, okay? We are not at the stage at the moment where we're doing climate engineering. We're not at the stage where we make massive changes in our climate. And one of the reasons for that is we don't know everything that we think we need to know to be able to do that correctly, okay? And so we're still in the study phase. Now, we're desperately trying to catch up. We're desperately trying to understand everything there is to know about how the climate evolves. But we're constantly surprised. And let me give you an example. Several years ago, the models would say we should be hotter now than we really are, than what we measure. We should be hotter. And that's because of the CO2 increase that's in the atmosphere, and that's a greenhouse gas. So why are we not hotter? Well, we just found out why. And it's due to the phytoplankton in our ocean. Okay? Phytoplankton is the very bottom of the food chain. They're one-cell animals that live in the ocean. They bring in the carbon dioxide, and then the zooplankton come up and eat them. Okay? And so as the zooplankton then falls to the lower part of the ocean, some of them get eaten by fish, but a lot of it falls down on the ocean floor, never to return to the atmosphere. We sequester or pull out that CO2, and it's laying in the bottom of the ocean in dead zooplankton. Now the CO2 that gets eaten by fish then get eaten by larger fish, and then, you know, that ends up on our table, and then, you know, the whole cycle is such that that CO2 gets released back in the atmosphere. That's part of that overall cycle. We're constantly amazed on how the Earth responds. And so we just got to keep understanding the processes. And so everything that changes the greenhouse gas input into our environment, we need to uncover, and we need to understand how it's doing it and what happens to those cycles and how that changes over time. We're not there yet. I wish we were, but we're not. So right now we're going to have to learn to live in a hotter world. I have to tell you that when we go in the past, there's been a lot more CO2 in our atmosphere than there is right now. The world has been hotter in the past. We've actually gone through a little bit of an ice age. 10,000 years ago, there were glaciers in New York. Okay? All that's eroded away as the entire planet is changing towards a warmer climate. Okay? Now, the biosphere is contributing to that because we are part of this planet, and that means life is contributing to it. No question about it. We just need to study it more. Okay? Okay. So yes, sir.
I would like to ask you, what's your advice for us, our new generation? And I would like to hear about you, from you, the secret of your success to being the chief scientist of NASA.
Okay, okay. So, yeah, okay. It's a great question. Right now is a golden age to get into science and engineering. Okay? Now, they're not necessarily money makers. Okay? I never got into the business I'm in because I wanted to make a lot of money. All right? So you have to be driven. If you want to be successful in anything you do, there's one key ingredient, and that's determination. Determination. Okay? I've never seen anyone that has succeeded without determination. Students that have the ability and and things are easy, if they don't have determination, don't actually succeed. Okay? I wasn't what I would call always a top student. I was good in a bunch of stuff. Sometimes I was the best. But it took determination for me to keep going. The stuff we do and the science and engineering that's necessary to do the things that look like absolute miracles, okay, are because these people are incredibly determined. They do miracles each and every day. And it's just spectacular to watch. And that is an adrenaline rush. As a scientist, I have discovered things that no one on this planet ever had known before. And I can realize that, and I can write science about it, and I can talk about it, and I can build my reputation, and that is a real rush. To be able to move the intellectual knowledge of this planet forward, for which others ahead of me may use to be greater heights. You know, I think it was Isaac Newton that said he stood on the shoulder of giants and to create Newton's laws, which are the fundamental basis of a lot of science that we do in physics. And he's right, absolutely right. And that process still continues. It requires all our effort to keep going. And that's the secret to my success. All right. Okay, we'll come down here, and then we got to get going back up there. Yes, sir.
Okay. So I really freaked out at the part you said that our Earth's magnetic field is dying or weakening. So my question is, considering climate change and other external factors, again considering the planet's magnetic field dying, when do you predict healthy human life will decline, not specifically be extinct, but our quality of life declining due to all these external and astronomical factors?
So we have a better quality of life than ever on this planet overall. I mean, the human race is doing really pretty spectacular. Now that doesn't mean everybody, and that means we need to really consider helping those that don't have the quality of life and continue to work in a variety of different ways. Indeed, our whole globe is changing. The magnetic field is going to switch, and how we believe it switches is the indications are the pole starts to move and the field starts to weaken, and both those things are happening. Now, it may take 1,000 years before the flip actually happens, but the rock record tells us it will happen, and the Earth will not have much of a magnetic field during the time of the flip, and therefore the processes of what's happening at Mars right now will happen here at Earth. So it's just a fact of life, and now we've discovered it. These are things that we need to keep discovering. Okay, I'll give you another important discovery that everyone should know about. The dinosaurs didn't have a space program, okay? And look what happened to them. 65 million years ago, they got absolutely wiped out by a 6-kilometer asteroid, okay? It's only 6 kilometers. So how many are out there? We have, over the last 15 years, been looking at everything that crosses our orbit, all the asteroids. And as I mentioned, 100 tons of material fall on this planet every day. We scoop it up all the time. And we have found about 970 planet killers that cross our orbit, things that we need to keep watching. Now, I don't want to frighten you again, okay? But it looks like we're going to be great for the next several hundred years, but we need to keep monitoring them, you know? Now that we know, we need to do that. Ignorance is not bliss. You know, parents out there, you wouldn't let your 2-year-old kid run in the street even though they don't understand what happens when cars go by, right? And so why would we be ignorant about our future of our Earth as it moves around the sun with objects whizzing by it all the time? Okay? Ignorance is not bliss when it comes to living on this planet. And so join in and try to understand what's happening. In 2022, we're launching a mission to an asteroid, and we're going to hit it and we're going to move it. All right? And we do that because we know someday we'll have to. All right? And that mission is called DART. Okay? Those are the kind of things we do. All right, let's go over here. Yes, ma'am.
I think everyone in this room, in one way or another, is concerned about education. Whether
yes.
you're a student, or you're a
yes.
professor, or administrator, or whatever. And what I want to know is, how does NASA decide what its priorities are, and how does that trickle down, I guess, to education? Because I look at, you know, my kid's pretty eager about astrophysics, and he's going to pursue that. And I know what I would do for him. But I look at the bigger picture and I say, okay, how does education keep up with what needs to be done? And how does NASA decide what needs to be done?
Yeah, so a lot of what I talked about, you're not going to see in any textbook for the next 5, maybe 10 years. Because this material is moving so fast. We're discovering stuff right and left. And so, if you want to keep up with what we're doing, I have a podcast. It's called Gravity Assist, where I talk to the top scientists in the field, and we talk about what they're uncovering. Things that won't be in textbooks for quite a few years, and they're just unbelievably exciting things. And at the end of the interview, I asked them, what was the event or the activity that got you excited, that accelerated you forward to become the scientist you are today? What was your gravity assist? Okay? Because that's how we use it. We use planets to change our trajectory and accelerate forward. That's the term. And it's all over the place. So from that, we recognize that it's not one thing, it's many things. And parents, we need to be sensitive about getting our kids a broad range of experience, because we don't know that event, whether it's talking to an astronaut or it's, hopefully being here and starting that path of being inquisitive and drive that gets you moving forward. To me, it was a high school teacher that gave me the opportunity to use a 12-inch Alvin Clark refractor, and I made all kinds of instruments and did astrophotography. And this island has wonderful opportunities going on in those areas, where there are telescopes that are being considered to be built on the mountains here, where there are astronomy clubs, where there's plenty of activities that they can get involved in. And we need to find those opportunities and let them do that. There are traditional educational objectives, and the schools do that well. What NASA can provide is inspiration, is see and have our kids see future goals and dream about them. If you don't dream about the future, you don't have a future, and you have to see yourself in that future to move ahead. That's what we want to have happen. Now, NASA has a very small amount of money. It's about $42 million that it uses in education across all of the United States. And so we have to be very careful on how we actually do this. Sometimes we'll cooperate with a variety of groups, like the public broadcasting system, and we do NOVA, and we get involved in these things. And then we want to use our embassy networks, and we want to be able to go to places and talk about the things that we're talking about today and keep that inspiration going. So give your kids experiences, because there's going to be one of them that'll come about where they'll put it all together and they'll go, I want to do this. I want to land that next rover on Mars, and it's going to be hard, but I can do it. Okay? Yes, sir. Okay.
Εγώ θα ρωτήσω μετά.
That's fine.
If we're able to plant different kind of plants on other planets, and estimatedly how much time will we be able to live there?
Good question. So we're just starting that research. As I mentioned, the Japanese Space Agency is moving in that direction, and so in a year, we'll get their initial results. Now, right now, we're growing lettuce on Space Station, and they're eating it, okay? So they're already, thinking about how you can grow plants in zero gravity, on station, and how what plants can grow in total water. We call that hydroponics, without soils. And so that some of that's really fundamental research that if we don't get going and do it, we won't know how it applies. So it's just the start of that process. Yeah, it's just the start. So a great field to get into. Yes, sir.
Σκέφτηκα να δυσκολέψω λίγο το ταξίδι, επειδή είναι πολύ έτσι ενδιαφέρον, και είπα να ρωτήσω, επειδή ασχολούμαι με τα μαθηματικά, πριν 20 χρόνια στην Αθήνα είχατε δαπανίσει αρκετά λεφτά ώστε να γίνει μία συναυλία, να το πω, σε συνδυασμό μαζί με έναν μαθηματικό και με ένα μουσικό, το Βαγγέλη Παπαθανασίου, όπου είχε γραφτεί μουσική. Και έχουμε όλους τυχαίως, μετά από 20 χρόνια, τη συγκεκριμένη αποστολή, να θέσω, δηλαδή, το ερώτημα μου είναι ότι σίγουρα δεν είναι τυχαίο το ότι θα γίνει το 2020, εφόσον ο δορυφόρος, βασικά ναι, ονομαζόταν Οδυσσέας και η επιστροφή του ήταν μετά από 20 χρόνια. Απλά θέλω να ρωτήσω αν είναι όντως τυχαία και είναι συμπτωματικά όλα αυτά.
Okay, so you're playing to my weakness. I'm horrible with languages.
So, actually your question is if there is a... η ερώτησή σου είναι αν 20 χρόνια μετά από μια... Oh, he talks about it in 2000. There was a satellite, Ulysses, that.
Yeah. Yeah. Yeah, we had a satellite named Ulysses.
Yes.
Yeah, it was a solar orbiter. It went out to Jupiter, got a gravity assist, changed the plane, and went over the pole. But it was really far away from the sun. And it was designed to measure the solar wind at all latitudes of the sun. So it was far enough away for it to discover many different things. One thing that it discovered that we really weren't sure was happening is even the polar regions of the sun are emitting solar wind. And in fact, the speeds are faster coming out of the pole than coming out along the lower latitudes. So Ulysses was indeed our first really great solar observer designed to measure the solar wind around. Now we're going to an area where it's generated, where it starts. And that's the next big step. Mm-hmm. Yes, sir.
As far as I know, the Indian mission to Mars, MOM, cost less than $300 million.
Mm-hmm.
Similar NASA Maven, I think, cost nearly $1 billion. What is different?
Yeah. Everything you said is true except for one word, and that is a similar mission. They're not. Yeah, one is far more capable than the other, okay? And that's the NASA mission. Maven is that mission. And it's a very extensive, very sophisticated mission that is still operating, like MOM is still operating. So these things, you know, these satellites that we do have certain capabilities that we build, and they're designed to make certain measurements. MOM was designed to make a set of measurements that were different than Maven, but we can relate them, and that's very important. So for us as scientists, the fact that we can obtain the money and build sophisticated satellites is great, and it allows us to correlate with other data. And we don't care what the other agencies pay. We're just interested in correlating, getting the data and correlating it. They did a marvelous job using their workforce and building a capability that was quite unique in Asia. And indeed, they were the first Asian country to be able to get a satellite in orbit at Mars, and that's just tremendous.
Are they using your DSN stations, the Indians?
There are a number of things that we did to help them, and some backup tracking and other things, yeah. But they're primarily doing their own thing right now, yeah. Now that they're in orbit, they're really in good shape. Now, it was designed as a technology demonstration mission. Not to believe, you know, that if it lasted 6 months, it would be wonderful. Well, it's going into like its third year. It's doing great. You know, it was really remarkable. They did an outstanding job. We're just delighted. Let me get going and work up the line here. Yes, sir.
It was very interesting to hear your opinion about extraterrestrial life. But I remember listening to an interview from the late Stephen Hawking saying that we shouldn't be too eager meeting alien life or intelligent life.
Right, he did. And I was being interviewed right after he said that in the afternoon. And the news guy went right to that, you know, and said, you know, what do you think of Stephen Hawking? And so I said, he's brilliant. Doesn't mean he's always right. But no, I didn't say.
Do you have a plan for that?
That's what I thought, but I didn't. I said the brilliant part, but I didn't say the other part. Yes, Stephen was a little worried about what we would find, but you know, we got to look. We got to look. Just the way that's going to go.
If I may ask another thing, do you think that humans that will be born in Mars, are they going to be able to travel back to Earth, or are they going to be, completely different from humans and not be able to live in Earth?
Yeah. So people that will be born on Mars, live, and stay on the planet, and then leave the planet, will have evolved differently than we will. Okay? They'll have different capabilities. Okay? In a whole bunch of ways. And so let me give you an example. We have microbiota. We have gut microbes that allow us to live and survive in this environment. We need them, okay, or we would die. On Mars, they'll be completely different. They'll be able to live in bodies and do different things because the environment is different. And that genetic makeup is just an example of how the evolutionary cycle will affect life over time. It has to. That's one of the tenets of life. It evolves. Okay? Yes, sir.
Is there any new ways NASA is finding new ways to propel a spacecraft, like new engines? What about the EM drive? I heard about a lot in 2015. Now I don't hear anything.
Yeah, so the ion drive that we're building right now is going to go on the Gateway. All right? So this is a fabulous engine, and it relies on a basic principle that for every action there's an equal and opposite reaction. So what happens is we have fuel on board, we take that fuel and we ionize it. That means we pop off some electrons. And then we run it through an electric field which accelerate those small particles and throws them out the back of the spacecraft. Okay? And that allows the spacecraft an additional thrust. And we keep doing this minute after minute, hour after hour, day after day, week after week, and we can build up enormous amounts of energy. So at any one time, the additional push the spacecraft gets is about the weight of this piece of paper. Okay? That's the little push it gets. But because we do it over and over and over and over and over again, we can accumulate that and we can push it faster. And our plan is to use ion engines going back and forth to Mars. That we believe will reduce the time. And the first big test of that will be around the moon in the ion engines that are going on the Gateway. Okay? Yes? Yeah, take the mic if you can. Good question. Yeah, are there any missions coming up that are going to look for exoplanets, extraterrestrial planets, planets around other stars? We just launched one in April. It's called TESS, and it's going to look at all the bright stars. And typically bright stars are close. And so it's already found the first set of planets. And so that's just the start of really exploring our neighborhood. I think it'll find 1,000 planets in the next couple of years. Those planets we're going to follow up with the Webb telescope. We're going to want to look at the atmospheres. And when we look at the atmospheres, we're going to want to see if there's oxygen there. We're going to want to see if there's methane there. We're going to want to see if there's fluorocarbons there that only intelligent life generates. Okay? And that'll give us a hint of whether these planets are habitable and whether they have intelligent life or not. So we're making some big steps in that area. We are. All right. Yes, sir.
Two questions, actually. The first one, your opinion. Do you think we will find intelligent life? That's one of them.
Yeah, I can answer that, yes.
Okay.
That's out there.
The other question, we see that to send a craft to Mars is going to require, from what we see on television, massive rockets with an incredible amount of fuel. To bring it back, to bring the astronauts that you're going to send to Mars, to bring those people back, is that possible?
Sure.
At this stage?
Yeah. Yeah, so here's what we're doing about that. Right now, we're going to land a rover on Mars, launching it in 2020 and landing it on 2021 that's going to core rock, okay? It's going to create a 3 or 4 inch long set of rock, and we're going to put it in a metal sleeve and lay it on the ground, and then we're going to have a rover come around, pick these up, and then bring them over to a Mars ascent vehicle. And the Mars ascent vehicle is going to take off and take those samples in orbit. That Mars ascent vehicle we're developing right now, and it's a start of a line that will increase over time, that will eventually be able to loft humans off that planet. Okay? And that's because we're doing it now.
So the first astronauts that you're going to send to Mars, will there actually be a program saying, yes, we're going to send these people for 2 years or for 6 months, and then we're going to send another craft after them to bring them back?
Yeah, good question. So, the way Kepler dynamics works in the solar system is that our planets, as they go around the sun, if you're closer to the sun, you move faster. Okay, so that's Earth. Mars moves a little slower. So every 26 months, they sort of line up that you can fire a rocket with whatever you want on it, and it will go cross Mars's orbit at the exact same time Mars is there, and then land on the surface. Okay? So it's like hitting a golf ball in New York and making a hole-in-one in LA. That's what we do. Okay, we can do that. And so that takes about 180 days. This is without ion engines, by the way. We can stay on the surface over 2 periods. The first period is the short stay, which is about 25 days. Okay? And then come back in the same window. The next one, the long stay, is about 390 days, and then it takes about 220 to 230 days to come back. That's the long stay. So when we commit to go, we're going to commit to the short stay or the long stay. Now, what will probably happen on the short stay is like we did on the moon, we'll have a vehicle in orbit and people on the surface, and then they'll be brought up and then they'll be taken back. This is why we need also ion engines to have the flexibility of breaking orbit and coming back and going back and forth to Mars. So those things are really being tested out, planned and tested out now in our lunar program. Okay? Yes, sir. This one right here.
You've been in the field for 40 years, and some positions you had to provide other scientists with data. And basically, you've seen the whole scene of big data coming to life in the past 25 years. How did data management changed over the course of 25 years, and in what point did NASA help about that? Did you help, or did you get the information from out of it?
Yeah, so there's really quite a fabulous relationship between the computer industry and NASA. You know, sometimes we engage them and they build some remarkable things that then they later market, and you end up with a cell phone. With fabulous resolution of images, for which we were already imaging using that same technology on previous spacecraft. So that relationship's really working great and has over the time. And it's a matter of investing in those things that we need and companies that find ways to use them elsewhere. So is that the heart of your question? That's going to continue. Everything we do in space in a variety of ways has some sort of spin-off associated with it, which is also makes it one of the most important economic generators, and that's well recognized. Yeah. Okay. Yes, ma'am.
I would like your interpretation of what gravity is.
Okay.
And how, if you consider it is if it is an engineering problem.
So gravity is incredibly important, and it requires mass. Okay. So gravity has a property where the masses want to get together. That's a mutual attraction. That's what builds planets. And so you have very small dust that's generated in the atmospheres of certain stars that get flung out into space and become part of a larger cloud that somewhere in there starts to condense and attract and create bigger and bigger lumps. Okay? And that's the start of new stars. That's the start of new planets. So from a seed, you can get huge planets if you have all the material you need and enough time to attract it and bring it together. So gravity is a concept that as you bring this material together, it increases over time. And the key part to that equation is the mass. Okay? All right, let's go over here. Yes, sir.
Kind of a particular reasoning behind the use of the last image on your last slide?
What, this one?
No, the questions one.
Got it. This one. Let me go back to it.
Yeah.
I love this image. I love this image. To me, things like science fiction are important. Things like creative art is important. It relates to what we do as scientists, okay? And so here is a young girl, and this young lady is creating her own solar system, all right? And we're finding solar systems that look like this with many planets of different sizes. It's just very creative. And those things I like. Yes?
Do you think we're going to be able to build our own...
Well, I'm sorry, put your mic on because I can't quite hear you.
Do you think we will be able to build our own planet one day?
Build our own planet one day?
Yeah.
Wow, that's ambitious. Sure, why not? Yeah. Yes, ma'am.
Are there any drawbacks in changing Mars' environment?
Are there any drawbacks? Oh, yeah, there might be some. And we need to be aware of them before we do it. And that may be, there may be Martians there now. Okay? And I would hate for us to go there and mess up the environment with a bunch of humans and destroy the life that's there. Okay? So we as scientists owe it to ourselves and the ethics of our discipline to thoroughly examine that environment to determine if there's life there or not today. Now, there may have been life there in the past, but not life today. And there may be life today just barely hanging on, but we have to know. And so we are indeed working very hard to make that determination. So there's so many things going on in this agency, as you can see, and that we have entire huge disciplines of work from looking at weird life. This is one of the reasons why weird life's important. Maybe there's weird life on Mars. We don't know. We don't even know what we're looking for. Except except this. Life has 3 attributes, only 3. Metabolizes, reproduces, evolves. And that could be weird life too, you know? And so that is just a fascinating area of discovery, and we just can't make discoveries fast enough to get caught up with everything that we need to. That's why we need more people, more scientists, more engineers to tackle some of these really tough problems. And they are exciting. They are absolutely exciting. Yes, ma'am.
May I ask, what is NASA saying about dark matter? Are there any missions
dark matter.
labs around dark matter?
Right. So let me mention what we mean when we say dark matter. When we step back and we look at our galaxy, and our galaxy's got arms, and we know that from our position within the galaxy, and we know that other galaxies that we see have that same configuration, and we look at those, and we see how they spin. They don't seem to spin and operate quite right. That bugs us for a long time. And then we figured out there must be some hidden mass, some type of mass that we can't see, that we can't measure, we can't figure it out, and that's affecting the motion of these spiral arms so that they do what they do. Because when we simulate them, by looking at all the stars and all the gas in these galactic arms, they don't operate the same way. So something's missing. And so in our primitive mind, we call that dark matter. Okay? We have several missions that are on the lookout for dark matter, indeed. And that requires some really important observations with big telescopes that are going to try to uncover more of the properties of dark matter to determine what it might actually be. So hang tight. We'll see if we can't solve that one too. All right, anyone else in that row? Let's go to the next row. Yes, sir.
Do you think that space travel can be the key for something else than just know there is life in other stars, like make fusion energy or time travel? And having in mind this and the previous equation about the future of rocket science, which is a better choice for someone who wants a career in astronomy, to start as a physicist or as an engineer?
Okay, in that respect, I think either one is appropriate. We have so many engineering challenges to tackle, and the scientists rely on the engineers to get them where they need to go. You know, when we landed Curiosity on the surface of Mars, many things had failed prior to that, and it was very difficult to do. And that was all in the hands of the engineers. They made that happen. But now that we're there, we're making all kinds of discoveries, you know. We're going different places. So I would say follow your passion. If you're more passionate about the engineering, that's what you need to do. If you're more passionate about the science, that's what you need to do. And you need to get determined, and you need to burn a hole in steel and move forward, and you'll be successful. Okay? So let me go up here. Yes, sir. Yep.
Yep. From the beginning 2000s, with each administration, the focus of NASA changes. So you had the Constellation project, then you had the Space Launch System to Mars, now you have the moon base to Moon, and then to Mars. And there seems to how does that prohibit the research in NASA? And is NASA focused now on this as a long-term plan, or will it just change for the next term?
Well, that's a really good question. So some of that may look like we change directions, but a lot of what we do is very well related. Each administration in NASA would like to make sure they have a vision for what NASA should be doing, but it's more the human exploration portion of it. The science portion of it is relatively intact and moves forward because we get advice from the National Academy of Science on what we're going to do, and Congress supports that and the administration supports that, and that enables us to continue on making progress in really focused ways that don't change when the administration changes. But the change of administration does happen, and that does change some things that we do. But right now, we have goals and objectives. Even in the previous administration, Mars was the ultimate goal. In this administration, Mars is the ultimate goal, but to test the things that we need to, we're going to use the moon as a proving ground. There was some concepts like that in the Obama administration, but they really came to be more well-focused in the Trump administration as we learn more about what we need to do to go to Mars. Okay? All right, the gentleman on the end. Yep.
Me? According to the Drake equation, there should be X amount of planets with life or intelligent life. The fact that we haven't seen any yet, that we haven't seen or they haven't reached us, doesn't that say either that this is not correct or that we are limited by, I don't know, general relativity and that we will never be able to reach them? And also a country like Cyprus that's so tiny, do you think that it can contribute to astronomy or astrophysics in any way?
Okay, so let me take the last one first. Absolutely. Absolutely. Stop shaking your head. Really, I'm serious. I was so impressed with what's happening in your schools and the dedication of students and the excitement of students that I think there's a huge future for Cyprus. Did you know the NASA Space Apps contest, which is a worldwide contest, Cyprus won the last 2 years in a row? It beat out everyone in the rest of this world. Okay, did you know that? Okay.
Matter of fact,
Congratulations. So the next Space
But on a
App
university level.
Yeah, the next Space App Challenge is tomorrow, and I'll be there. It's also one of the reasons why I'm here, is to congratulate the teams and tell them onward to higher heights. Okay? All right. Yes, sir.
One query. With a long duration of life out in space in zero gravity, won't that have an effect on our biology, on how we're actually made up, on the way that the blood actually gets transferred through the vessels?
Yeah.
And on the return journey back to Earth, how would it actually make? How would we actually be able to live there again, since all our muscles have not been trained in order to be able to survive in such conditions after such a long amount of time?
Okay, those are all great questions. And we don't have the answers to those, but we're working on them. But it sounds like you might have the ability to get the answers that we need. Now, what's happening in space is several things. Microgravity is such that our body and our muscles, we lose muscle tone, but we also lose bone strength. It's like osteoporosis. We have that here on Earth, but it happens in space. To whether you're a male or a female, doesn't matter, okay? But we're finding with a regimen of exercise, we can and the right drugs, and these are osteoporosis drugs that we have here on Earth, we use those in space, that we can abate that a little bit. But we haven't even started doing the research in artificial gravity, and we're going to start doing that. So artificial gravity may actually solve a whole series of problems that will enable humans to stay in space for long periods of time with very little or no effect on their body. So it's just another line of research that we're doing. It'd be great to have you come join with us.
Furthermore, in iron engines, for the last I heard of them at least anyway, you guys used to use ionized particles to be ejaculated outside of the engine via those magnets, which only work under sub-zero conditions. But those ionized particles are actually superheated. So how have you managed to combat its effect?
Okay, so we're doing that right now on a spacecraft called Dawn. Dawn was launched in 2006 and has 2 ion engines on it. They've been working great, and it's currently orbiting Ceres, and it's running out of fuel. But we know we have tackled all those engineering problems. Some are real, some are not. We know how to do it. Now we're building the bigger engines. Okay? Yes, next to him.
Can you see methane-powered rocket engines in the space of the future of space engineering?
Yeah, methane's a potential fuel, and it may have a role to play. I don't know. Research is being done in a whole series of propulsion techniques, and I don't know that we're doing that at the moment. I don't know that methane is something they're researching.
But as far as I know, we can refuel the engines using methane from other planets. I think you mentioned a moon of Jupiter. I don't remember the name, but had a lot of methane.
Yeah, a lot of the outer planets do. Indeed, you're right. We are real keen on using resources that are out there rather than take everything with us. Yeah, we are. Yes, ma'am, right here. Yep.
Will be there in the future, you think there will be any mining on the moon?
Great question. Yes, there will. What we see on the moon on the surface are platinum group metals. Platinum, palladium, iridium, a whole series of very important metals are on the moon in various locations. Now we know where they are and where they're coming from. They're not coming from the moon. They're coming from asteroids that impact the moon, and that material is laying on the surface. Okay? So the moon is actually a great reservoir for some precious metals. So I anticipate that in the future, as more companies decide to go into space and mine that material, that it will be possible and it will be used. Now the first use of that will be probably in space. We'll need that material as a resource to do something in space. And the reason why I say that is, at least right now and for the foreseeable future over the next several decades, it's not economically viable to bring the metals back to Earth. It costs more to bring them back than pay the market price. That may change, you know, and if it does and it becomes economically viable, that's what we will do. You know, it's all economics. Okay? So let's go, okay, you've asked a question. There's so yes, ma'am, let's do this one.
My question is kind of not scientific, but it's more of your personal life. So what would be the most difficult or the most challenging decision you had to make as a scientist, and specifically as a NASA scientist? It's a tricky question, right?
No, it's a great question. As head of planetary science, I managed several $1 billion a year of money, and I had to make some tough decisions. One of the toughest decisions I ever made was not launching Curiosity in 2009 because it wasn't ready. It cost me and the U.S. population, the people that support NASA, $495 million, okay? But I knew that if we did try to launch Curiosity in that window, the probability that it would fail was great. 26 months later, we cracked all the problems. I was confident we could land this 1-ton rover down on the ground. I was so confident that I decided we needed to bring the entire nation with us. We had plans to film the live in the control room and interview people. We opened the channel for museums. We broadcasted on Times Square. There's so many people that know about Curiosity's landing because we let them in on that process. My boss at the time said, why are you doing that? Wonder if it fails. Okay, wonder if it crashes. You'll embarrass NASA. But I knew that we did everything humanly possible to land this spacecraft on the surface. And I felt supremely confident in the engineers that did it. Okay? And I was right. Okay? That decision was a good one. And we've been bringing as many people in the public along with us as possible. And we've been quite successful. But I have to tell you, that may not always be the case. Some days we may fail. But it's not from the lack of trying. And it's not from the lack of trying to figure out how to do these things right. We want to do them right. But we just don't know everything all the time. Okay? And it's really what makes the business fun. Yes, sir.
How did some of the disasters that happened with like Challenger or Columbia, I don't remember.
Horrible things.
Yes, how they
people.
affected the program or the course of NASA's plans or canceled whole projects.
Yeah, it did.
Or you kept, trying to find the solution and keep on.
We did. The latter is correct. When we failed and people died in Challenger, we really spent a significant amount of time stepping back and trying to figure out what we did wrong and how to fix it. And that took a long time. That took actually a couple of years before we got back into business. And then we methodically solved those problems. And, we all have to learn by doing. And what we'd like to do is do everything right, but human nature is such that we can't always do that. What's really great about the American people is their understanding of that concept and allowing us to sometimes fail. It's not because we want to, it's because that's what happens. But, it's like falling off a horse. If you're ever going to learn to ride, you got to get back on it. And going into space is something we have to do. Okay. Yes, sir.
It's more of a hypothetical question. If, let's say, extraterrestrials have at least the same technology as we do.
Who does?
The extraterrestrials.
Oh, yeah, E.T. Okay, yeah. Uh-huh.
If they have the same technology as we do, and they study our atmosphere, what will they see and what will they think about us?
Okay, so what I did with the spacecraft about 5 years ago, the spacecraft was called Deep Impact, and it had already flown by a comet, dropped off a huge mass, hit the comet, cometary material sprayed all over the place, and we got to look at it for the first time. Really exciting mission. And now it's done, and it's floating around in the solar system, and I thought, oh man, this is what we need to do, because it's got several beautiful instruments on it. I said, wait until Deep Impact is as far away from the Earth as it can possibly be, 1 pixel, and then stare at that pixel and get a spectrum, okay? Now, why did I want to do that? Because when we look at exoplanets, it's going to be 1 pixel, okay? I want a Rosetta Stone of a living planet. what does the spectrum look like? Okay? So we stared at the Earth to acquire the light, to create a spectrum that we then can identify water and methane and oxygen and all those things. And all of a sudden, that spectrum started to change. We're going, what the heck is going on? We found out that it was changing based on the percentage of clouds, water, and land, because the Earth was spinning. Wow! We now have a Rosetta Stone of a living planet with clouds, water, and land. Okay, that was pretty neat. And then it changed again. What the heck was that all about? The moon moved in front of the Earth. Okay, and now we know what the signature is of a planet with a moon. Okay, those are the kind of things now that we have in place that will allow us to compare with exoplanets of whether they are living planets or not. We did the same thing on Venus. We did the same thing on on Mars. And so now we have what I call the Rosetta Stone of possibilities. We're ready to go. Okay? Yes, sir. And we're all out of buttons, right? Okay. All right, so now that we're out of buttons, let's go for 5 more questions. 1.
I wanted to ask if NASA plans to use quantum computers and what it will use.
Oh, absolutely. Yeah, quantum computing is big.
And what benefits it will have?
That's a good question. There are several plans, and I'm not completely up on those. But we already made some big announcements, and there are several NASA centers that are going to get into it big time. I mean, every new revolution in computing we've seemed to bring in and utilize. The concept of parallel processing really started with Beowulf computers. Those Beowulf computers were developed at NASA Goddard Space Flight Center. And so we've been at the heart of a lot of computing revolutions. How they're going to be used, I really can't tell you. I'd love, you've sparked my interest. I'll find out. I like that question. Okay. Yes, sir. Number 2.
Should we be afraid of solar flares because they could affect our communication systems or our modern technology systems?
That's a really good question. Right now, there are some types of space weather we are ill prepared for, okay? And we know it. And we have to convince a number of industries to protect our power grids from these kind of storms. Many of them will not do that. And the reason why they won't do that is they look at it in probability. It's, these superstorms that could knock out all the power in huge regions of the country for many, many months at a time, forcing us as a population to give up electricity and go back 100 years in time and try to live the way our fathers did in that. That is of concern. But that's rare. They may be, every 100-year events, okay? Maybe sooner. And that's a long time. And so spending money to wait for a single event a long time away is not necessarily economically viable for them. And so many of these companies are making decisions not to protect the grids the way they should. And that's a mistake. And we may learn to live to regret it, okay? So, don't be afraid, be knowledgeable. Don't ignore it, be an advocate. Study it so that we can talk about it in the right way and we can get the results that we need because it's important for our life. Okay? Yes? You're so lucky you got 2 of them.
Is it possible that we might have contaminated any of the planets we have visited?
Yes, good question. yes, we probably have, in some small ways, contaminated some planets that we have visited. Yeah, and we worry about that. We worry about that. One of the things that I did last year during the Great American Eclipse is to determine if microbes from Earth that are on our rovers that land on Mars could survive, okay? And we tested this during the solar eclipse, this whole idea. And here's how we did it. 50 balloons were going to be launched along the path of totality, and they were going to go up to 120,000 feet, okay? And they were going to look down, and they were going to see the shadow cross the country. 120,000 feet on this planet is the same pressure and temperature of the surface of Mars, okay? And during the eclipse, when some of the ultraviolet light gets blocked, it's about the same amount of ultraviolet light that Mars receives on its surface. So we went to clean rooms where we developed these spacecraft, and there's a particular little bug. It's called it's a thermoduroneuron, but there's another little preface that goes with it. Penna something thermoduroneuron. You know, I'm not a biologist, but it's a nasty little bug. Not because it's hazardous to our life. It's benign, but we have a heck of a time killing it. And so we want to clean off all our rovers so that they are as clean of microbes as possible. And I can guarantee you there's some of these on Curiosity. So we created 2 strips of this bacteria. One we put on 37 balloons, and the other one we kept as a control. We launched the balloons, and then we recovered safely 26 of them, and they're in the laboratories now being analyzed. But it looks like the environment is pretty tough. And over time, they may not survive in that environment. But we don't know that until we do these kind of experiments. And then that gives us an idea of how we may be contaminating other places or not. And so long as Curiosity didn't roll over, you know, and that the wheels we protected such that they were ultra clean, and we left them ultra clean, and that's what touches the surface, we're probably in pretty good shape. Probably in pretty good shape. But those are the kind of things we have to think about when we launch our missions to other planets that we don't want to infect. Yeah, that's a great question. Yes, sir. 4.
I would like to go a little bit back to the magnetic field and the problems that are going to be created. We're taking for granted that this is going to happen, and there are not even science fiction thoughts of let's see if we can slow down the process or reverse the process or do something about it?
Yeah. We can't slow down the process. We don't know how to do it. We're sitting here watching it happen, okay? The currents are deep in the inside of the interior of the Earth, and what we think happens is in the outer part of the core, the nickel-iron currents that are running around creating the Earth's magnetic field all of a sudden roll over the pole. They keep moving in the same direction, but when they roll over the pole, that flips the dipole. That flips the direction of the magnetic field. We see that in the rock record. That's exactly what's happened on this planet many times. It's going to happen. Okay? Can't stop it. But at least we know it's going to happen. All right? That's half the battle. Knowing is always half the battle. So we need to make careful measurements, we need to do more modeling, and we need to determine, is it going to be in 50 years or 100 years or 1,000 years or 10,000 years? And then once it flips, how long are we without a magnetic field? Now, there's still a little magnetic field that's there, but it may not be much of any protection until it grows again and then begins to protect the Earth. So we have a lot to learn. We have a lot to learn in that area. Okay, number 5. Number 5, let's go to this gentleman here that is absolutely got to ask a question.
Good evening.
Hi.
Is NASA developing ways to incorporate AI, artificial intelligence, in its future vehicles?
You bet.
That's number 1. Number 2, are you guys developing new means of communication with your vehicles?
Yes.
New networks, like 4G, 5G, even more. And are you guys cooperating with DARPA? Thank you.
Okay. 3 questions. So, yes. So let me take the last yes. We work with a variety of agencies that are also doing a variety of research science. And DARPA is one of them. So the type of communication that we're already tested and seems to work out great in space is optical comm, where we're going to transmit data in infrared light, okay? And not these long radio waves, really small waves. We can pack a lot of information in them. And we did that with a optical communication system on a mission called Leventis that we launched to the moon. Worked great. Little bitty telescope about this big, pumped out about 800 megabits a second. Just piling the data out. Worked great. Now we want to take it to Mars. Okay, and we actually have it on a spacecraft that we're building that will fly by Mars, but even go further. We'll go out in the asteroid belt. And that mission is called Psyche. And it's going to an asteroid called Psyche. And now your first one, AI. Every generation of spacecraft we make will have more and more intelligent computers, okay? And that will lead the way. And so that leads me to a question this gentleman asked that I forgot to answer, and that is, what about life out there? How come they haven't communicated with us? If we look at what we do, what NASA does and other space agencies do is constantly put in their missions more and more intelligence, and then send them out. And we do that because they can operate in extreme environments for long periods of time, and so long as you provide the power, they are our eyes and ears. All right? I can imagine a civilization that wants to contact us or probe us. The first thing they will do will send artificial intelligence here. Yeah, they won't show up first.
So it's going to be...
won't be little green men, it'll be their robots.
Their AI versus our AI.
They'll be their AI versus our AI.
Like future wars.
And that brings us to science fiction. Okay? 2001 Space Odyssey, okay? Where there's Hal and the crew going out to find aliens, and the crew is looking for life like them, but so is Hal. Hal is looking for life like it, which is the most advanced AI. And I think what Arthur C. Clarke was trying to say is, Hal found it first. No, he didn't malfunction. He just didn't need the bags of water getting in the way anymore. Okay? Okay? You never see the aliens in the movie or in the book. You always see environments that are created, you know. And of course, human ingenuity screwed that up. All right? And that's the way it goes sometimes. Thank you very much. Thank you. Thank you. All right.
That was an amazing I would like to thank thank the speaker one more for this inspirational talk. We'd like to thank also the embassy, the US Embassy, once more for this event, for making this event happen. Give us so much information, so much inspiration. Thank you very much.
All right, before you leave, I would like to thank the school for allowing me to come and spend valuable time doing things that I dearly love, which is talking about what we do, all right? So here's a little token of my appreciation, and I will sign it.
Thank you.
All right, thank you. I had a great time. Thank you. Thank you very much.